at LJ Institute of Engineering and Technology. Today we are going to start a new topic, that is improper integrals. So let's begin with the definition of improper integrals. The integral a to b f of x dx is called improper integral if one or both the limits of integration are infinite, or if the function fx becomes infinite at a point within or at the end points of interval of integration. So in all, there are three types of improper integrals. So let's study the first type, that is improper integrals of type 1. The integral a to b f of x dx is called an improper integral of type 1 if either lower limit or upper limit or both the limits are infinite. Okay, so let's understand this by example. Now you can see this integration minus infinite to be 1 upon 1 plus x square dx. You can see this infinite in the lower limit. So whenever you see an infinite in the lower limit or upper limit or in both the limits, okay, so such types of integrals are known as improper integrals of type 1. Now in the second example, you can see infinite in the upper limit. Okay, so this is an improper integral of type 1. Also in this integration, you can see infinite in both the limits, right? So this is also an improper integral of type 1. Now let's study improper integrals of type 2. So it is a definite integral in which integrand becomes infinite at one or more points within or at the end points of the interval of integration. So let's understand this with the help of example. Now we have this integration 0 to 1, 1 upon x dx. Now the limits are not infinite, but if you substitute x is equals to 0 in this function f of x, that is 1 upon x, okay. So this term will goes to infinite, okay. So it goes to infinite at this end points, right. Also, let's consider this example. Now here the function is what? 1 upon this x square minus 1. Now this denominator will become 0 at which point x is equals to plus or minus 1, right. And this plus or minus 1 lies between this interval minus 2 to 2, right. So this is the improper integral of type 2 because at these two particular points your integral will goes to infinite, okay. And here also if you will substitute 4 over here, so denominator will become 0, so this term will go to infinite, okay. So this integrand becomes infinite at this particular point, okay, at the end of this interval. So we can say that these integrals are improper integrals of type 2. Now we will study improper integrals of type 3. Now here it is a definite integral in which one or both the limits of integration are infinite and the integrand becomes infinite at one or more points within or at the end points of interval of integration. So this is the property of improper integral of type 1 and this is for improper integral of type 2. So what we can say that it is a combination of improper integral of type 1 and type 2, right. So let's see the example. Here we have integration 0 to infinite 1 upon x square dx. Now you can see infinite in the limit, okay. So this is an improper integral of type 1 and if you put x is equals to 0 over here, what will happen? This will goes to infinite, right. So it is also an improper integral of type 2, right. So we can say that this is an improper integral of type 3 because it is a combination of type 1 and 2, okay. Now let's study example. Evaluate integration 0 to infinite 1 upon x square plus 1 dx. Okay, so here you can see infinite over here, right. So this is an improper integral of type 1. Now let's evaluate this integration. So integration 0 to infinite 1 upon x square plus 1 dx is equals to, now wherever we have this infinite, we have to substitute t. Okay, so we will write as limit t tends to infinite integration 0 to t 1 upon x square plus 1 dx. Okay, now we will evaluate this integration. Okay, so you will get the answer as limit t tends to infinite. Now integration of 1 upon x square plus 1 will give you tan inverse x and the limits are 0 to t. Okay, now we will substitute the limit. So tan inverse t minus tan inverse 0, and this limit t tends to infinite as it is. Okay, and we know this answer of tan inverse 0 is 0, and when t tends to infinite, so here you will get tan inverse infinite, and the answer of tan inverse infinite is pi by 2, right? So the final answer of this improper integral is pi by 2. Okay, now we will see one more example. Evaluate integration 0 to 3 1 upon under root 9 minus x square dx. Okay, so if you will put x is equals to 3 over here, right? So this denominator will goes to 0 and this whole term will goes to infinite. Okay, so we can say that this given integral is improper integral of type 2. Okay, so we will evaluate the integration. So integration is what? 0 to 3 1 upon under root 9 minus x square, right? Now at this point 3, our this integration is going to infinite. Okay, so we will suppose this 3 as t, right? So we will write as limit t tends to 3 integration 0 to t 1 upon under root 9 minus x square dx. Okay, now we will evaluate this integration. So what you will get answer? Limit t tends to 3 here. The integration of 1 upon 9 minus x square, it will be sine inverse x upon 3, right? And the limits are 0 to t. Substitute the limits, so you will get limit t tends to 3 here. Sine inverse t upon 3 minus sine inverse 0. Now we know the answer of sine inverse 0 is 0, and if you will substitute 3 over here, so you will get sine inverse 3 upon 3, that is sine inverse 1, and the answer of sine inverse 1 is pi by 2. Okay, so the final answer of this improper integral is what? Pi by 2. Correct? Now let's move to one more example. Here we have to evaluate integration 0 to infinite 1 upon x square dx. Okay, so you can see infinite over here. So it is an improper integral of type 1. Also, if you put x is equals to 0 over here, so this will goes to infinite. So it is a improper integral of type 2 also, right? So it is a combination of type 1 and 2. So we can say that this is an improper integral of type 3. Okay. Now we will evaluate this integration. So integration 0 to infinite 1 upon x square dx. Right. Now we get infinite answer at 0 and we have this infinite also. So what we will do? We will write integration in two parts. So integration 0 to 1 upon x square dx plus integration 1 to infinite 1 upon x square dx. Okay. Now we will solve firstly this integration, that is integration 0 to 1 upon x square dx. Give it a name I1. Okay. So here we have infinite answer at this 0. Okay, so what we will do, will suppose it as c1. So you will get limit c1 tends to 0 integration c1 to 1 upon x square dx. Right? Now we will integrate this. So what you will get? Limit c1 tends to 0 integration of 1 upon x square is what? Minus 1 upon x, and the limits are c1 to 1. Okay. Now we have to substitute the limit. So what you will get? Limit c1 tends to 0. First, in place of x, substitute 1. So you will get minus 1, and minus minus will become plus. And in place of x, substitute c1. So you will get plus 1 upon c1. Okay. Now as c1 tends to 0. Okay. So as this goes to 0, this whole term will goes to infinite. Right. So the answer of this integration I1 is what? Infinite. Now we will solve I2, that is integration 1 to infinite 1 upon x square dx. Okay, so we have infinite over here, so we will suppose this as c2. So we will write as limit c2 tends to infinite integration 1 to c2 1 upon x square dx. Now firstly we will evaluate this integration. So what you will get? Limit c2 tends to infinite integration of 1 upon x square is what? Minus 1 upon x, and the limits are 1 to c2. Okay. Now first substitute the limit. So what we will get? Limit c2 tends to infinite minus 1 upon c2 and minus minus, so plus. In place of x, substitute 1, so you will get here 1. Okay, now apply this limit. So limit c2 tends to infinite, so 1 upon infinite, so this term will goes to 0. So what will remain is 1, right? So this is the answer of I2. Now the final answer of I, that is I1 plus I2. Okay, now the answer of I1 is infinite and the answer of I2 is finite. So the combination of these two answers is what? Infinite. Okay, so we have the answer as infinite for this improper integral. Okay, now we will study a new topic, that is direct comparison test. So if fx and gx are two continuous functions for x greater or equal to a, such that 0 less or equal to fx less or equals to gx, then this integration a to infinite f of x dx converges if this integration a to infinite g of x dx converges, and integration a to infinite f of x dx is less or equal to integration a to infinite g of x dx. Okay, so we have this condition that this f of x is less or equals to g of x. Okay, and if this g of x dx integration a to infinite g of x dx converges, then this integration a to infinite f of x dx will also converge. Okay, now we have another condition that if fx and gx are two continuous functions for x greater or equals to a, such that this fx is greater or equals to gx, and then what we can say that integration a to infinite f of x dx diverges if integration a to infinite g of x dx diverges. Okay, so here we have this condition, and if this integration a to infinite g of x dx it is divergent, then what we can say that this integration a to infinite f of x dx will also diverge, right? Now we will study one more test, that is limit comparison test. So if fx and gx are two continuous functions for x greater or equals to a, such that fx is greater than 0 and gx is greater than 0, and this limit extends to infinite f of x upon g of x is equals to L, and L should be between 0 to infinite, means the answer of L should be finite and non-zero term. Then this integration a to infinite f of x dx and integration a to infinite g of x dx both converge or diverge together, right? So firstly what we have to do, we have to find this limit, and the answer of this limit should be a finite and non-zero term. Okay, then what we can say that this both the integral will converge or diverge together, right? Now let's begin with the example. Is the convergence of improper integral 1 to infinite cos x upon x square dx, right? So here what we have, function fx as cos x upon x square, and we have to suppose gx, so we will suppose gx as 1 upon x square. Okay, why we are supposing gx as 1 upon x square? Because we know that this cos x is less or equals to 1. So if you divide it by x squared to both the sides, so you will get this condition that cos x upon x squared is less or equals to 1 upon x squared. So we have this form that fx is less or equals to gx. So what we have to do, we have to solve this integration 1 to infinite gx. Okay, and if this gx is convergent, then we can say that this fx will be convergent by a direct comparison test. Okay, so we will evaluate this integration 1 to infinite g of x dx, right? The gx is what? 1 upon x square, right? Now this is an improper integral of type 1 because we have infinite in the limit, right? So we will suppose this as b. So we will get limit b tends to infinite integration 1 to b 1 upon x square dx. Okay, evaluate this integration. So what you will get? Limit b tends to infinite minus 1 upon x, and the limits are 1 to b. Substitute the limit. So what you will get? Limit b tends to infinite minus 1 upon b plus 1. Okay, now as b tends to infinite, this whole term will goes to 0. So what will remain? 1. Okay, so the answer of this integration 1 to infinite g of x dx is what? 1, right? So what we can say that this integration 1 to infinite 1 upon x square dx is convergent, right? And therefore by direct comparison test we can say that this integration 1 to infinite cos x upon x square dx is also convergent. Okay. Now we will solve one more example. Check the convergence of integration 4 to infinite 3x plus 5 upon x raised to 4 plus 7 dx. Okay. So here what is given function fx as 3x plus 5 upon x raised to 4 plus 7. Okay, now we have to suppose gx. So how you will suppose gx? Here function is given 3x plus 5 upon x raised to 4 plus 7. Okay, take out x common from the numerator. So you will get here 3 plus 5 upon x. Okay, and take out x raised to 4 from the denominator. So you will get 1 plus 7 upon x raised to 4. Right? 1x will get cancelled. So what remains? 1 upon x cube. So we will suppose gx as what? 1 upon x cube. Right? Now we will find the limit. That is limit x tends to infinite f of x upon g of x. That is equal to limit x tends to infinite. This function fx and this function gx. Now we will use the same procedure. Take out x common from the numerator. Take out x raised to 4 common from the denominator. Okay. So this x cube and x, that is x raised to 4, will get cancel out. So what remains is this. Okay. Now if you will apply this limit x tends to infinite, this 2 term will goes to 0. So what remains is only 3, which is a finite and non-zero term. Okay. So what we will do, we will find this integration 4 to infinite g of x dx. Okay. So if this integration is convergent, then the given function will be convergent, or if this is divergent, then the given integral will be divergent. So let's solve this integral, that is 4 to infinite g of x dx. Now the function gx is what? 1 upon x. Okay. Again, this is an improper integral of type 1. So we will suppose this as b. So you will get limit b tends to infinite integration 4 to b 1 upon x cube dx. Right. Evaluate this integration. So what you will get? Limit b tends to infinite minus 1 upon 2x square 4 to b. Okay, substitute the limit. So you will get limit b tends to infinite minus 1 upon 2b square plus 1 upon 32. Right? Now, if you will apply this limit b tends to infinite, so this whole term will goes to 0. So what remains is 1 upon 32, which is a finite term. Right? So what we can say from this, that this integration 4 to infinite 1 upon x cube dx is convergent. Okay, and by limit comparison test we can see that this integration 4 to infinite 3x plus 5 upon x raised to 4 plus 7 dx is also convergent. Okay, so I hope you have understood throughout the session. Thank you for watching.